Hi everyone, this is Les with Team PyTorch, and today we're going to go over how to work with distributed checkpoints, otherwise known as local state dict. So the difference here, if you've seen the other tutorial where we go over full state checkpointing, full state checkpointing will generate a single individual file. Distributed or local state dict checkpointing will actually save lots of files, like potentially thousands, into a single directory, and so the directory itself will be your checkpoint. So the advantage and the reason for that is that when you have all these small files that can be streamed during the saving, and so as a result we don't have the concerns over overflowing CPU memory. So distributed checkpointing is excellent for gigantic models, like think 175 billion, for example. Those would typically exceed CPU memory on a server, and so by doing distributed checkpointing, we can avoid that because the whole entire thing will be streamed. And so that's the big advantage. So let me show you first what that looks like. So over here I've got a single file just saved out with full state dict, so deepfit1.pt, and that's your typical, what you're probably accustomed to, a single file for your model checkpoint. By comparison, if we go up to distributed checkpoints here, so I've got a 1.5 billion parameter model saved out here, and so what you have is your metadata file that's going to kind of coordinate everything, and then of course what you'll see is just lots and lots of these GUID files with no extension, and that's actually your checkpoint. So that kind of shows you the difference there. So let's get into the code and show you how to work with this. So as usual, I'm running with nightlies. This is July 19th. And a couple imports that you'll need, obviously FSDP, and then we're bringing in here the state dict type. Oops. And the reason for that is we're going to key off of that in the code so we can make sure that we're working with the relevant checkpoint, just to not have any confusion there. You also need to bring in this file system reader and writer, and then these two functions, to save state and load state dict. So once you have those ready, I've got two simple functions here to show you. So if actually let's start with save. So save distributed model checkpoint. It's going to bring in our model. The rank is really just to print out stuff. All ranks need to call this. But the first thing that I've got here is we're going to check and make sure that in fact we are working with the local state dict or distributed checkpoint. Again, you don't want to have confusion between the two. And then once from there, we can set up our directory name or folder, and we'll pass that to create a file system writer. So we've got our writer, and then we go in with a context manager here that will basically set things up with the model and local state dict, and then all the ranks will effectively call this. And then we'll have our save state dict, which will write everything out, as you saw, and you'll end up with this very large in terms of quantity of individual files over there. So that's the saving here, and then let's get to loading. It's obviously pretty similar in terms of being an inverse. Do want to check again that what we're working with is a local state dict. We create our folder name. I've just got a little check to make sure the directory exists. And then from there, it's file system reader as opposed to writer. Same thing with the context manager. And then we're going to go in. It's pretty much similar aspect here. And at that point, you are loaded up and ready to go. A couple of quick notes for larger models. Again, 20 billion plus. This is where CPU memory can start to become a problem. This is where distributed checkpointing really shines. Distributed checkpointing itself is actually more efficient in terms of the network and so forth. But the one wild card is it can lag because it's writing out thousands and thousands of tensors, and that's where it's a little bit dependent on your hardware. So you may not necessarily get the full benefit of the efficiency there. I have seen that it's pretty common that it's slower on writing out for the larger models, especially compared to full state dict. But again, at least in this case, where to make the proper choice in terms of if you're going to exceed CPU memory, you only have one choice, and then beneath that you can kind of compare and contrast the two. Last thing I'll mention is that the only identifier in distributed checkpoint is that metadata file, what I've shown over here. And so the one problem is if you do want to be very, very clear that you're iterating your directories when you're saving your checkpoints, In other words, don't save them into the same thing or the same directory, because what will happen is you'll end up overriding this metadata file. The GUID names will change, and you'll end up with basically twice as many files, but it's actually only a single checkpoint. So that's just one thing to be very aware of, to be very cognizant about how you're iterating where you save your checkpoints with distributed checkpointing. So that's the quick summary. The code will be on the notebook here if you want to pull that and leverage that for your own work, and hope that helps.